Hi and welcome to today's video. Today we are going to introduce the notion of a matrix. Now, basically we already know what a matrix is. You've noticed that we have worked with tableaus for systems of linear equations. Well, those tableaus were basically an arrangement of numbers in some rectangular form. You will surely have noticed that tableaus and vectors are very similar. The difference is vectors are usually arranged in just one column, whereas tableaus have several columns. So you could also say a tableau is a collection of vectors. And the name matrix formalizes this idea. So from now on, what is currently known as a tableau to you will be referred to as a matrix. We'll start with a formal definition of a matrix. We'll introduce some important operations, and then we'll collect some important properties before we go deeper into the theory of matrices and matrix computations. So the section is called Matrices. And the goal of this and the next few videos is to formalize the notion of a tableau under the new name matrix and introduce corresponding operations. Let's start with the definition. We'll define what a matrix is, basically by just saying it's a collection of numbers in a rectangular form, and we have two numbers that specify how many columns and how many rows this rectangular form has. So there's really not more to that. Let m and n be natural numbers, and those will be the number of rows and of columns. M is usually the number of rows, n will be used for the number of columns. And of course, we need one entry for each position in that rectangular grid, and we call those aij. So let aij be in R for I in M, so 1 to M, and J in 1 to N. Then the following is called a matrix. We usually denote matrices by capital letters, or if we want to name their elements, their entries, we will write them in this form. And if you want to stress the range for the indices, we might also add the indices here. So we can write something like I in M, J in N. We'd often leave this out if it's clear from the context how many rows and how many columns that matrix has. And what that means is a rectangular scheme like this. So in the first row of this scheme, we have an entry A11, then we have A12, and so on up to A1n. So the first index always denotes the row. A1 something is always an entry for row 1, and the second index denotes the column. So A12 is the index for row 1, column 2. So that means for the second row, all the entries will have an index of 2 in the first position. So that's A21, A22, and so on up to A2n. And that goes on for m rows in total. So the last row has index m, am1, am2, and so on up to amn. So this here is called a m by n matrix. That's written as m, and then this times symbol, this x symbol, times n matrix. The entries of that matrix are called entries, of course, or components, or coefficients, or elements, and we'll use those interchangeably. So with entries or components or coefficients or elements. And those are the Aij. There's also a handy abbreviation for the set of all matrices of a certain dimension. And that is written as, similar to the vectors, R to the m by n. So the set of all m by n matrices is denoted as R to the m by n. So if I write a matrix is an element of R to the m by n, that immediately clarifies how many rows and how many columns that matrix will have. Now, for a given matrix, we will always speak of not just the entries, but also of the rows and of the columns of that matrix. So we need to formally clarify what that is. And it is what you would expect, of course. A row is just a vector that corresponds to one row in the matrix. A column is a vector that corresponds to one column in the matrix. So formally, for a given matrix A with entries Aij, where I is in 1 to m and j is in 1 to n, so that matrix is in R to the m by n. The row vector that consists of the entries A, I1, A, I2, and so on up to AIN. So the I, the row index, is always the same. And that is a vector in R to the n. That is called the ith row of A. And of course, you can do the same thing for the column vector. The column vector that consists of the entries A1j for some given j, A2j, up to AMJ. And that column is a vector in R to the m. That is called the jth column. Of our matrix A. And of course, we'll also have to define when we will consider two matrices equal. And basically, that's the same thing as for vectors. For matrices to be equal, all the entries have to be equal. And for the entries to be comparable, of course, the matrices have to be of the same size. So the number of rows and columns has to be the same. So that's part 4 of that definition. Two matrices A with entries Aij in R to the M by N, and B with entries Bij in R to the R by S are equal, and we'll denote this as A equals B if and only if M equals R, N equals S, and Aij equals Bij for all I in 1 to M and all N in 1 to J. Now there's a set of matrices that is special in one aspect, in that it has the same number of rows and columns. Matrices of this kind will appear fairly often, that's why they deserve their own name. A matrix that has the same number as of rows and of columns will be called a quadratic matrix. So a matrix in R to the N by N, so that means the number of rows is equal to the number of columns, is called a quadratic matrix. And then we'll introduce one operation for matrices that we'll fairly often require, and that is the transposition of matrices. The idea is basically, if you have a rectangular scheme, then you can just flip that scheme by exchanging the rows and the columns. So if you write each column of the original matrix as the row of a new matrix, then you obtain a matrix that has its dimensions flipped and its entries flipped accordingly, and that matrix will be called the transpose. So formally, what we do is the following. The transpose of a matrix A with entries Aij in R to the M by N is the matrix A transpose. We'll denote this by a T superscript. And that is simply the matrix where rows and columns change their roles. So that is composed of the entries A, J, I, where now J is the row index, formerly used to be the column index. So this new matrix has n rows and it will have m columns. What that means is, once again, we take the original first row of A and write it as the first column of A transpose. So the first column of A transpose is then A11, and then A12, A13, and so on up to A1n. So that used to be the first row of A. That's now the first column of A transposed. Second column of A transposed is the second row of A. So we get A21, A22, and so on up to A2n, and so on. So The last column is the last row of A, which is A, M1, A, M2, and so on up to A, Mn. So this is the transposition, and the result is now a matrix in R to the n by m, right? So you'll notice the indices have flipped. Okay, and finally, one more name for special quadratic matrices, the matrices that are quadratic and that have the property that their transpose is the same as the original matrix. Those sometimes play a very special role. Those matrices are called symmetric. So a quadratic matrix is called symmetric if A transposed equals A. And you know this only works for quadratic matrices, because if the matrix is not quadratic, then the transposed has different dimensions from the original matrix, so we can't compare those. They cannot be equal. For a quadratic matrix, that could be the case. And there's one more thing. The matrix might also be skew symmetric. That's almost the same thing, but the sign of the entries also flips when you transpose them. So skew symmetric means the transpose of the matrix is equal to minus the original matrix. Okay, before we go on, let's have a look at a few examples to clarify these. First, let's have a look at a matrix that looks like this: 7, 1, 3, 0, 3, 4. We'd like to transpose that matrix. So the transpose of that matrix, what does that look like? Well, what we do is we take the first row of this matrix and write it as a column. So we get 7, 1, 3. It's the first column of the transposed matrix. Now we take the second row of the original matrix and write it as a column, as the second column of our new matrix. So that's the column 0, 3, 4. And this is the transposed matrix here. And you'll notice this is in R 3 by 2, 3 rows, 2 columns. Whereas this original matrix, 7, 1, 3, 0, 3, 4, that is in R 2 by 3. 2 rows, 3 columns. Okay, let's have a look at some quadratic matrices next. So the matrix, for example, this matrix here, A 1, 2, 4, 2, 1, 2, 4, 2, 3. That is a quadratic matrix. So we can ask if that matrix is also symmetric. And if we transpose it, let's see. If we transpose that matrix, again, we take the first row here, write that as a column. The second row here, we write that as a column. And here's the last row, and we write that as a column as well. And if you compare the results, you will notice that this is exactly equal to the original matrix. So this matrix is indeed a symmetric one. And what that means basically is that the entries of the matrix are symmetric with respect to the diagonal of the matrix. So if I draw this diagonal here, is here, you will notice that I can flip the elements on the diagonal. So here's the same entry, here's the same entry, here's the same entry. So that means symmetric basically means symmetric with respect to the matrix diagonal. Let's see an example of a skew-symmetric matrix. So if we take the matrix 0, minus 2, 4, 2, minus 4, 0, minus 2, 2, and 0. And if we transpose that, what do we get here? Well, the first row becomes the first column of our new matrix. The second row becomes the second column of our new matrix. And finally, the last row becomes the third column of our new matrix. So that is how the new matrix looks like. And you notice that if we take out a minus sign here, then we get 0, 2, minus 4, minus 2, 0, minus 2, and 4, 2, 0. And that is exactly equal to the matrix that we started with. So this is an example for a matrix that is quadratic and skew-symmetric. And again, if you look at the matrix, you can identify this property again by looking at the entries flipped along the diagonal. So if you compare these entries here, you will note that one entry is exactly the negative of the other. And that means the matrix is skew-symmetric. And finally, of course, there are also matrices that are quadratic, but neither symmetric nor skew-symmetric. So here's an example. Let's write the first row like this, 1, minus 2, 1. If you want this to be non-symmetric, then we just have to look at the diagonal once again. Now we have to look at the flipped entries. So for example, here's the minus 2. If we want this to be non-symmetric, we cannot write, or we should not write a minus 2 in here. We've destroyed that property. And if we also not write a plus 2 here, it cannot be skew-symmetric anymore as well. So we just put a 0 here, and it's all destroyed, right? So, and it doesn't really matter how we fill up the rest. Let's just do something, right? So this is a matrix that is quadratic, but neither symmetric nor skew-symmetric. Okay, that's been a lot of definitions. There's unfortunately a little more to come. One other special kind of matrices are the so-called diagonal matrices. Generally, matrices with lots of 0 entries will be of interest later on. And one particularly interesting kind of matrices, because it's so easy, is the diagonal matrices. Those are matrices that have non-zero entries only along their diagonal. So let's formally define that. Part 1. A quadratic matrix. Again, we need quadratic here, because for a non-quadratic matrix, the diagonal doesn't stretch all the way from the top left to the bottom right. And it's not really clear what the diagonal actually is. For a quadratic matrix, that is clear. So a quadratic matrix, A equals Aij, is called diagonal matrix, or just diagonal, if the entries Aij are 0 for all I that are not equal to j. So the entries on the diagonal are exactly the ones where I and j are equal, have the same value. Those can take on any value, all the others need to be 0. That's the definition here. So Aij equals 0 for all I not equal to j. There's a nice shorthand for writing diagonal matrices. So a diagonal matrix with entries, let's call those lambda 1, lambda 2, and so on, up to lambda n. Those are real numbers. Is written as, just write diag, and then you put in the entries on the diagonal. What that means is that's the matrix that has the lambdas on its diagonal, like this, and zeros everywhere else. Yeah, so there's a 0 block here on top, and another 0 block here on the bottom. And that's an n by n matrix. And one very special diagonal matrix is the one that has only ones on its diagonal. Those matrices will be called identity matrix. The reason for that name will become clear in one of the later videos when we deal with matrix multiplication. So this is part 2 here. The n by n identity matrix, or sometimes called unity matrix, is defined as, the shorthand for this identity matrix is usually IN, and that is just defined as the diagonal matrix of the all ones vector, where we have n entries. So in other words, ones on the diagonal and zeros everywhere else, like this. Yeah, so that's a matrix in n by n. It is denoted as IN, EN, sometimes EN instead of IN is used. That comes from the German term Einheitsmatrix, which is a German term for identity matrix. Or sometimes it's just denoted by I or E if the size is not important or if it's clear from the context. Again, a few examples of diagonal matrices. Simple example for a diagonal matrix here. let's take diagonal matrix with entries 5, 0, 1. And notice that 0 is not forbidden here. 0 is explicitly allowed on the diagonal. So this matrix has the entries 5, 0, and 1 on the diagonal in this order. And all the rest is 0. Right, so this vector here, that's the important part, 5, 0, 1, that is composed of these numbers here. And part B, let's look at a few identity matrices. For example, the identity matrix I2 is this one here, 1s on the diagonal, 0s everywhere else. The identity matrix I3 will look like this. And hopefully you'll notice that the columns and the rows, both of the identity matrices, are unit vectors. So the columns and rows of identity matrices are unit vectors. Finally, I already announced at the beginning that we were going to formally define what a tableau is. We now have this formal definition under the name matrix. So it's time to replace our old tableau notation by our shiny new matrix notation. And that's the final definition for this video here. So let's just define that replacement. Now, if we have a system of linear equations in tableau form, that looks like this, for a system of linear equations of the form AB. In tableau form, both A, so this left-hand side coefficients, that is a matrix, and also A with one additional column, and that one additional column is B. So what that means here is A with additional column B on the very right. Those are all matrices, of course, and they have names. They are called, first, the coefficient matrix. So A is called the coefficient matrix of a system of linear equations. The coefficient matrix. And A with the additional column B is called the extended coefficient matrix. Of the system of linear equations. And one last thing we need to transfer over from the world of systems of linear equations and their tableau form. We defined a rank for a system of linear equations. And of course, we can't just transfer that definition to matrices by saying, well, the rank of a matrix is equal to the rank of the tableau if we regard this A as the coefficient matrix of a system of linear equations. So for a matrix A in R to the m by n, the rank of A is defined as the rank of the system of linear equations where A is the coefficient matrix, and the right hand side doesn't really matter for that, but just put 0 here. And the notation is that rank is denoted by, or simply, rank of A, as we already used it before. Okay, so from now on we will not speak of tableaus once more. We will only speak of coefficient matrices and extended coefficient matrices of systems of linear equations from this point on. That concludes our introduction of matrices. In the upcoming videos, we're going to deal with operations on matrices of different kind and with properties of matrices and the matrix spaces. I'll see you then.